Okay, so this is our second half of the lecture. Hope you guys had a good break. Okay, so let's begin with discussing maybe one really nice axiomatic system, or some rules at least of constructing axiomatic systems. So, there's my marker. Okay. So, one of the most prominent axiomatic systems that was constructed was the one made by, if I remember correctly, Georg Cantor, prominent set theorist. He created two really nice and neat axioms, which he used to prove some stuff, including cardinalities and infinity. And I believe that was extensionality and power set. Yeah. And there were some other ones, including union and stuff. But the thing is, when Bertrand Russell examined his theory about extensionality, I believe, axiom on extensionality, he noticed a paradox. Right. So it's not really extensionality, but it was another axiom. So there was an axiom. So Bertrand Russell came into the scene after Georg Cantor made his neat little axiomatic system. What happened was that he tried to, so there was a relation saying that, okay, for a condition over a variable x, I can construct another, there is a corresponding like relation, right? That makes that statement true, right? So if I have a variable x, it is true, or I can construct another set which is x prime that makes x's truth value 1. Okay, so Bertrand Russell examined the case on what if x and x prime are one the same, and what if now our condition is membership, okay? So x now, so what we're saying is that, okay, previously we can say that x can be true if and only if x prime is true, you know? So if only if x prime is true. So now we're saying, okay, x is an element of itself, or x prime, if and only if, well, x prime, the elements of x are part of x prime. So now we're saying that x is an element of itself if and only if x is not an element of itself. And that's a paradox. So this is Russell's paradox, I believe. Let me just review it a bit. Let me see if I got it right. Sorry if I'm pausing a little bit here. Okay, so so this is all put, the paradox is all put in the barber's paradox. So a barber is tasked with, cutting the hair of every man who hasn't groomed himself, right? Yet. So he's tasked with, cutting the beard or shaving the beard, cutting the hair, just nice, just neatly, for those who haven't groomed themselves. Now the question is, what about himself? What if he's not groomed as well? So does he do it for himself? Well, it is stated that he doesn't groom. So does the barber groom himself as well? Well, who grooms him? Who's gonna groom him if he's, but the barber cannot do it if he's certainly not groomed, So there's a paradox there. I don't know if I'm getting this right or not. Please do correct me in the comments if I did get this part wrong. Okay. So yeah, that was Russell's paradox, and it ended all hope for Georg Cantor's very neat axiomatic system. So that's one thing we need to note, is that we've noticed time and time again that every axiomatic system that we possibly tried to construct will have paradoxes in it. Okay? Now, much time later, Ernst Zermelo came into the scene. So, Ernst Zermelo. And he introduced 6 more conservative axioms which did away with, Russell's paradox. Hey, if you guys don't know by now, an axiom is basically a fundamental assumption that we make that is true without proof. If a theorem requires us to prove that it is true by showing that constituents of it is it's rightfully so as stated in the theorem, an axiom is something we just assume without proof. It is evidently true without us having to show that it is true. Now, if an axiom is provable, that technically just becomes a theorem, and that. And the axiom is basically the pillars of everything. We need the axioms to prove the theorems that follow in our theories, of course. And one of the most, Zermelo's axiomatic system, which we call now ZFC. And in fact, it wasn't just Ernst Zermelo. There was also Frankel, some guy named Frankel, who contributed to it, and they created ZFC, which is Zermelo-Frankel axioms with choice. Okay. All right. Now, there are various types of axioms that we can discuss about. We're just going to discuss some of them. Yeah. So, some closure axioms. Okay, so the first one is the axiom of extensionality. I mentioned this a while ago. And this states that distinct sets have distinct members. And the important takeaway from this axiom is that if I have 2 sets that are exactly the same, so I have a set X and a set Y, and I give them an equivalence relation that is precisely equal, then we're saying that each member of X and each member of Y are exactly the same. So this is stated in here, so X and Y are only true if and only if for all X in X and for all Y in Y, X is equal to Y. For 2 sets X and Y, such that they're only equal, or both of them are only exactly equal when every element inside them are exactly the same. So an example of this is that the naturals are equal to the naturals, of course, because 1 is 1, 2 is 2, 3 is 3. And 4 is 4. Now you can tell me that what element from X and Y, you can say get 1 and then I can get 3 and then equate them, right? The thing is, that's not how it works. What we're talking about here are 2 elements which we claim to be exactly the same, right? Now, because these 2 are exactly the same sets, this X and this Y here are essentially just the same thing. Okay, in order for us to show that these 2 are the same, or that N and N are the same. Okay. Now, after we discuss about axioms, that's when we actually go and construct our number sets, or our sets, which is the natural numbers and the reals. That will come in the next lecture. Okay. Most notably the piano axioms, which is, oh man, it was a wild ride when I learned that. Yeah, and all that stuff. Okay, so that was extensionality. So the next one. Okay, so by extension, if I have two ordered pairs from this and this, so think of this as a two-dimensional space and this is a two-dimensional space. If those ordered pairs are exactly the same for every, ordered pair inside these two spaces, these two spaces are the same. Or if x and y are some n-dimensional space and they have exactly the same members or tuples or n-tuples of elements, they are exactly the same. Or this equivalence relation holds. Now you may be telling me, oh well, since it's an equivalence relation, you need to show that it's reflexive, it's associative, it's stuff like that. But this is what we just assume, or this is just what we assume. Of course, it's an axiom after all. We don't need to prove it. Okay, so the second one now is pairing. Pairing. And this one states that for so for all x and for all y, there exists a z such that for all w, w is an element of z. So z is a set now. Actually, I'm gonna use a big Z so that it's not confusing. Big Z. If and only if W is inside X and W is inside Y. So actually X and Y here are sets. Sorry. Not elements. So in set theory, we express sets in terms of big letters and elements as small letters. So W here is an element. So now what we're basically saying is, what we're establishing is the existence of some element that exists in two, I suppose what we call the intersection of a set. Intersection of two sets. Z here is basically what we call the intersection of X and Y, because we notice that every W that's inside Z is only inside Z when it is in either X and W. So it is inside either their union or their intersection. Next is the sum set. So the sum set establishes the existence of what is called the union of sets. If this is intersection, sum set gives us the union of sets. So the best way of showing this is via Venn diagrams. I have one set here, another set here. This part here is the intersection. So I'll call this A, and I'll call this B. This part here is A intersection B. You've seen this Venn diagram pop up in everywhere in logic, and it's always what you see whenever you talk about sets. Okay, so this part here is A without B, or A set minus B, and this part here is B without A. The entire thing is A union B. And the notion of this was encapsulated in pairing. Now we're gonna make or construct this notion via the sum set. Okay? Okay, so the sum set states that for all x, there exists a y, or for all big X, a set, there exists a y, big Y, not small y. There exists a y such that there exists a Z such that for all W, just Z, for all Z, such that for all Z, Z in Y, or Z is only in Y, if and only if there exists a W such that Z is in W and W is in X. So W is some subset of X. Yep. So now Y now is denoted as the sum set of X, or cup X. So what we're saying here is just we're taking the union of every subset of X, right? So for all X, there's just a Y, a set Y. This is for all Z, Z is in Y if and only if there exists a W, a subset in X that Z is a part of, and W is a subset of X. So so Y is that sum of all possible W in X. So that is that sum set. Next one is asunderon, or separation. This is my favorite one. Asunderon. So what this basically is telling us is that any subset of a set is a set. The formal way of defining this is that for all big X and for all W, I don't know why they use vector notation, but I suppose that's just notation. Yeah. There exists some Y, big Y, such that for all Z, Z is inside big Y, if and only if Z is in big X and satisfies some formula phi. I'll use bar phi because that just looks like the null set. Phi or phi or Z and W or vector W satisfies this formula. So phi here is a formula. Phi is a formula. I have to press phi. Okay. Okay. All right. So next is one of the most important ones, especially in person theory. This is very important, especially in person theory and constructing topologies. This is the power set. Oh, you already know what this is. This is mathCalP, that good old set of all possible subsets of a set. Yeah, power set. Okay. So it's formally stated as follows. For all sets X, there exists some set Y, such that for all Z, X, Z is in X. Sorry, Z is in Y. Y, if and only if wait, what? if and only if Z is a subset but not equal to X. This terminology is a bit weird because we can either think of Z as an element or as a subset. But yeah, that's a Sunderong. Oh no, not a Sunderong, power set. Now, a noble thing to say is that the power set of X, mathcal P of X, is bigger than X. So it is, in terms of when we say or talk in terms of topology, we're saying that this is strictly finer. This is strictly finer or coarser, finer than X. So the power set of X is strictly finer than X, and this is why we're saying that the topology of a given set is strictly finer, or it can be finer than the set, because most of the time we use the power set for the topology. Okay, power set of X, its cardinality is bigger than the cardinality of X itself. Or if we use sharp notation, sharp power set X is bigger than sharp X. So that's one thing to note. And this is called Cantor's theorem. I'm not going to prove it here, but it's an important thing to state that obviously the power set is bigger than the set itself. Okay. Okay, so the axiom scheme of replacement. Now this is a bit complex, so I'm not going to discuss it just now. We're going to skip that for the time being. And we're going to move on to the empty set. Yeah, this one. This one's also very important. This establishes the existence of what is called the null set, which is denoted by like this. It looks a bit like phi, but there's a specific LaTeX command for it that differentiates it from phi. Besides, we also have the var phi, so we can use that instead of just regular phi. So this is called the null set. It's basically the set that contains nothing. An important rule is that any set A union the null set just equals A. And A intersection the null set gives us just itself the null set. Now, I need you guys to note now that here in logic, in formal logic or in foundations, there won't be much intuition that will go around. So if you guys find like a big wall of symbols boring or it's not intuitive to you, just sort of bear with me, because that's how we formally do things in pure mathematics, or at least at the base or the foundation of it all. It's like starting with the ugly stuff and then we get with the beautiful stuff at the end of the rainbow. Yeah. Okay, so the axiom of the empty set is as follows. There exists an X such that for all possible Y, Y is not an element of X. So X is now a set, right? X is a set, not really a... However, just as the empty universe is a null for all axioms up to but including the axiom of empty set, we find that a universe in which every set is finite can be a model for all those axioms and the axiom of empty set. So this basically means we don't have quite all the axioms that we need just yet. Since there are at least some sets that are infinite, such as, well, undoubtedly infinite, like the naturals or the real numbers. Hell, even the real numbers, hell, even the rationals are really big, but their infinity is much smaller than R, of course. Because we can fit all of the rationals into just numbers like 0 and 1. We can fit all of the rationals in between that interval. And R would be infinitely bigger than that, like much bigger. Now, another thing we're going to talk about here in foundations is infinities. I believe I talked about this in femboyology, especially when it comes to omega. Yeah, definitely. No, not femboyology, femboy theory. yeah, or position theory. We talked about omega. So this foundations is definitely where we're gonna go in depth with that, right? And also von Neumann universes and stuff like that. Okay. So axiom of infinity, there is an infinite set. All right. Now we established the null set. Let's establish quite the contrary. If we have nothing, we can have everything, and that is exactly the axiom of infinity. There is an infinite set. So one can think of the axiom of empty set as and the axiom of infinity as being two messages of the same kind. So the universe is non-empty. It's not. There's nothing. It's not nothing. Our universe is not nothing, obviously. And the universe is really, really non-empty. Right. So yeah. Well, the thing is, the very neat thing is that, although it sounds a little bit circular in argument, we can prove the existence of the null set, right? Oh no, X here is just the null set. X denotes the null set. X denotes. Let me write that down. X denotes the null set. Okay. Or it's rather the converse. So this denotes X, which is the null set. All right. We can prove that this exists via extensionality. We know that if, according to extensionality, by some extension of logic, no pun intended, if a set exists, obviously its subsets exists, right? Now, because the null set is nothing and its subset is technically nothing and nothing exists, then obviously it exists. So there exists a null set. We can frame this as a theorem and prove it using extensionality. Now you may be telling me, oh, well, saying nothing exists is a bit oxymoronic. But the reason why it isn't quite oxymoronic is that it's a funny footnote, is because we're talking about symbols here. We're not really talking about real quantities per se, but we're talking about sets and how certain things like, well, a set that contains absolutely nothing is an actual object. So let's suppose that this space that I am holding in my hand is absolutely nothing. There's no particles in it, no antiparticles or particles coming together and annihilating, but just nothing. I'm holding it. It exists in real life, even though it's quite nothing. I'm holding nothing. So it's quite a bit, it's not quite right to say that it's not right that we should have nothing here, or that zero doesn't exist. You know, it's quite, in the beginning, it's quite a stupid argument already. Okay, so for those arguments, just throw them out the window. We're talking about mathematical rigor here and not always application in real life. So actually that ends the second part of the lecture. I think I'm just gonna splice this in the video editing software. Yeah, I'll just splice in the video editing software here because I accidentally exited it. So I know this lecture isn't quite long as compared to other lectures, such as of course, in position theory or in algebraic femboid theory. So yeah, in the next lecture, we will actually begin constructing number sets, such as the reals and the naturals, but mostly the naturals. And then we're also going to investigate how it is with respect to some algebraic properties, like how it forms a monoid, I'm not really monoid, but how it forms a magma, and something like that. We're going to be investigating, taking a detour. And of course, we're also going to be constructing the basis for all of our theories, especially for position theory and for femboid theory, most specifically femboid theory. I know femboid theory works over position theory, so it's all based on position theory, and so we're making a bedrock for position theory. That's for the next lecture. So yeah, that's a good place to stop.